So, we are starting in on Unit 6, Gravity and Circular Motion. So we're going to be covering the topics of Newton's law of universal gravity, some applications of gravity, we get into circular motion, and then eventually into planetary motion, satellite motion, and orbits, um, kind of how things orbit around each other. So Newton didn't discover gravity, and one of the legends is that he got bonked off the head while sitting under an apple tree, and I had that aha moment, discovered gravity. Well, that's not true. What actually happened was he was pondering, could the same force that made an apple fall out of the apple tree be the same force that was keeping the moon in orbit around the Earth? So he was the first person to synthesize the idea that gravity acted at such a great distance that that's what held the moon in orbit and what made apples fall. Through his initial idea, though, what the law of universal gravity was, he realized that that force had to be proportional to the product of the two masses and inversely proportional to the square of the distance of separation. Okay, so that meant he came up with kind of this little definition here, that force was proportional to the first mass times the second mass divided by their distance squared. Okay. Now, if you notice, it's not equal to at this point. So to make it equal to, he had to think, well, maybe there's just some constant there. And that's exactly what he did. He just threw this idea of big G. So it's known as the gravitational constant. Now, Newton himself didn't bother to find that gravitational constant, big G, which makes the force of gravity between any two objects, big G, this constant, times mass 1 times mass 2 over d squared. It was another scientist by the name of Henry Cavendish who did an experiment where he looked at the gravitational attraction between two very small masses that were just hanging and two stationary masses and watched how they rotated to figure out that G was roughly 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. And that's everywhere in the universe. That constant holds true. So now, once you get this idea that the force of gravity between any two objects, so this is between a star and a planet and its moon, you and the Earth, any two objects on Earth really, is that the force of gravity will be big G m1 m2 over d squared. But one of the main things here is that we need to realize that it's an action-reaction pair, right? Newton's third law. So the force on object 1 is the same force on object 2, just they're in opposite directions. All right. So now the idea of the force of gravity on you from the Earth, well, you're also putting a force on the Earth. The difference is, though, the force on you, because you have such a small mass, causes you to accelerate at 9.8 meters per second squared downward towards Earth. The Earth is so large, though, that when you put that same force back on Earth, it doesn't accelerate upward at a noticeable acceleration. Okay, the acceleration is so small, it's negligible. So gravity decreases with this idea of that inverse square, 1 over d squared. What's interesting about this is it means that gravity continues to act at a distance as far away as you go. But it also means that the closer you get, the force gets more and more attractive. So the closer the distance between the two objects is, the greater the force. The further it is away, the force gets weaker and weaker and weaker, but it never reaches zero. Because anything over infinity still isn't zero, it's still some very, very small value. It approaches zero, but it never actually reaches zero. Another interesting fact with this idea about the forces being vector is that they can be added together. And when you add vectors together, we call this superposition. So the superposition of the forces. So like right now on Earth, there's multiple forces on Earth, right? There's the attraction between the Earth and the Moon. There's also the attraction between the Earth and the Sun, right? There's the attraction between the Earth and all the people on the Earth, even though we could be considered part of Earth. All those forces add together to give you the kind of net attractive force. Now, why I bring this up is this really great thing that is important to us, especially here being in a coastal town, which are ocean tides. So we're used to dealing with the fact that there are two tides each day, right? 2 high tides, 2 low tides. So we get that full cycle of really 2 tide cycles, right? The 2 tides each day, a high and a low, a high and a low. And that comes from the attraction of the water, on Earth to the moon, right? So I've got the moon over here. It's attracted to the Earth, but that water is also attracted to the moon. And that makes that bulge in the ocean's waters, which causes the high tide bulge, right? And roughly, because the Earth is rotating, and the moon doesn't move that fast, because the moon only goes around the Earth once every 28 days, that bulge takes about 12 hours to go from bulge to bulge, because it takes 24 hours to go around the Earth, or for the Earth to rotate. But we have these things called astronomically high tides. Well, what does that actually mean? Well, what that means is that when we have a new moon or a full moon, we get this alignment that we have up top here, okay? Sometimes referred to as an astronomically high tide as a spring tide, because what happens is you get a pull of attraction between the moon and the Earth, and then you also get a pull of attraction between the sun and the Earth. And I know I just kind of overdrew this one here a little bit, so let me make it a little smaller here. So there's 2 forces pulling it this way, all right? Now, granted, you wouldn't think the sun would have that much more of an effect, but it's got enough of an effect to add another, 6 inches to a few feet of tidal effect, depending on where you are in the world. And that 6 inches to a few feet could mean a significant difference in, your high tide. Now, halfway through the month, when you have your half moons, so halfway between full moon and new moon, the moon is actually kind of pulling the water this way, while the sun would be pulling this way. Well, if you understand kind of the idea that they are vectors, right? So if we've got a force this way, a force this way, the net pull is actually kind of this way. So we don't get as high of a high tide. We get kind of a more even tide mid-month. So we call these a neap tide. So the high tides are not as high, the low tides are not as low during the mid-month tides. So that's why we get, some storms, if they sync up near a full moon or a new moon, we get a lot more erosion on the beaches, right? Because you've already got a higher tide plus storm surge makes it that much more aggressive to the beaches and the erosion. Whereas if it occurs mid-month, because we're at that neap tide, you don't get as much of an effect as you would during the spring tide of the astronomical cycle. So this gets us to talk about the idea of gravitational fields, because that moon being around the Earth, or the Earth going around the sun, we could be at different positions around, the sun different times of the year, but we're still attracted to it. And that's because we can start thinking about this idea of being in a gravitational field. Okay, it's not like it's just a single direct point-to-point relationship. So it's like we're altering the space around the Earth. Another example of a force field that's a little easier to visualize is a magnetic field. So if you've ever seen a magnetic field where you put iron filings around that magnetic field, you can kind of see the field lines of the magnetic field. I know it's a great thing they always do in like elementary or middle school. They'll put the magnet to the paper and sprinkle the metal down. So with the magnetic field lines, or even now in our case the gravitational field lines, you get these lines that seem to radiate towards an object. So in our case, gravity seems to radiate towards Earth. Okay, so at any point you are away from Earth, it seems like you're being pulled towards Earth, and you're being pulled inward towards Earth. Right? It's not like the Earth repels you away, the Earth attracts you in, so they point towards Earth. And then the closer that they seem to get together here, so if you notice they're closer here than they are out here, it's because you have a stronger force when those field lines are closer together. Now, another interesting thing is if we kind of plot the gravitational fields for a planet, and I'm even going to plot to the point where we're inside the planet. So if I started kind of inside the planet here, right down here in the center, I should actually have no gravitational field at the center of the planet. And you're like, well, why would I have no gravitational field? Well, that would be because I'd have an equal amount of mass around me in all directions. So I'd be pulled to the left, to the right, up, down, at whatever angle, equally. So the net gravitational field, when I add up all those forces, should be 0. So if I was in the center of the Earth somehow, miraculously, even though it's a molten core, I should be able to just kind of float there, kind of cool, because I'd be attracted equally to all parts of the Earth. And then as I slowly move towards the surface, as I move out here, 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 I've got more mass to this side of me, then I get more mass to this side of me. So I start to have more of an attraction to one side than the other. So I start to have kind of a linear field effect happening within the Earth, all right? Which is why it looks up here to kind of be linear, okay? But then once I get outside of the Earth, that's when that whole, force of gravity equation starts to govern it. The whole big G, m1, m2 over d squared. So in this case, they're using r as our distance. So they're saying how many radiuses of Earth or radiuses of the planet we are away. And you see it starts to drop off kind of as a nice curve, exponential decay, because that 1 over d squared relationship. So another interesting thing that could happen is, what if we had another hypothetical planet that we could just drill a hole perfectly through? Okay, and let's say it actually is an Earth-like planet, so that at the surface, our acceleration due to gravity was g. Well, if I'm halfway down through that planet, the acceleration would be half. Then if I was at the center, like we said before, it'd be 0. Then if I got through, it would be back to half. But again, remember that we're always being attracted kind of towards the center, right? So here I'd be attracted towards the center, towards the center, towards the center. So what would happen? Well, I'd start to oscillate. So basically, I'd be falling this way, then I'd turn around, I'd fall this way, I'd fall this way, I'd fall this way. I would just keep falling back and forth and back and forth and back and forth and back and forth if I fell down this hole. So it'd be kind of a cool thing. You'd fall down the hole, and then you'd pop out on the other side of the planet, and then you'd fall right back down the hole again. Whee! All right, so now we're going to start our next kind of section on circular motion. So circular motion is the idea that our path now is no longer a straight line. So up until now, most of our paths we've looked at have been straight lines, or we've looked at parabolas, which is the fact that we've got linear motion in like the x direction, but we're accelerating in the y, so when we plot it, we get that nice parabolic curve. But what happens is when we move in, a circular path, right? So if I'm moving around like this, circular path, something has to cause that path to form, right? Because if you remember, Newton's kind of first law says that things like to continue on, at a constant velocity, which means constant speed, constant direction, unless acted upon by an outside force. In this case, we're going to assume that our v is constant. Okay. All we're changing is our direction, because I'm going from here, now this would be v, here would be v. So I'm just changing the direction. So to change the direction, I'd have to have some force pushing it inward. And that force pushing it inward sometimes is labeled as FCP or F sub r. I like to use F sub r for force radial because it's pointing along the radius, that we call the centripetal force or centripetal acceleration. All right, and if we do out all the math and do all the derivations, we find out that that acceleration radial comes out to be the velocity squared over the radius. That will tell me how much acceleration I need to keep myself going in that circular path. And that acceleration is perpendicular to that velocity, right? So if the velocity is this way, the acceleration, again, it's perpendicular, would be this way to cause the curve, the nice circular path. So now we know if we have the acceleration, force is mass times acceleration, so the force radial will be equal to mass times velocity squared over r, all right? Now something has to cause this force, right? It's not like it's its own new force. So it could be caused by gravity. It could be caused by a string, if you're holding on to like a ball on a string. It could be caused by friction if you're in a car going around a curve. So there's numerous forces that can cause this force radial or the centripetal force as you're going around a curve or going around a circle. The reason we need to start understanding this is we start to think about things like Einstein's theory of gravitation. So he started thinking about gravitational fields as warping space-time around the planet. Okay. So imagine if I took a ball and put it into a sheet. All right. You'd think at every radius away from that distance that you'd have the same acceleration inward, right? If I was to roll some object in, right, like this, it might catch and follow one of these lines and just keep orbiting and orbiting and orbiting and orbiting, right? Or if I was to roll it in just right here, it might orbit out here, right? Because it's going to be kind of following that path where the acceleration kind of being caused inward relative to whatever velocity I give it will keep it going. Now, if the velocity I give it isn't enough, right, so I come in and I'm not going fast enough, it'll do the death spiral. And if you've ever been over to the mall, they've got that big coin kind of fountain, they call it, that if you roll the coins in, it kind of looks like this, and it's that little vortex going down, and because the coin's not going fast enough, because it loses some speed every time it goes around, it does the death spiral down the hole. So, black holes. Black holes come about because gravity happens to basically become too great for even light to escape. And how that happens is, back to the idea of force of gravity and then that force kind of radial piece. If the light gets to that point where it can't go fast enough and it gets pulled in and kind of gets sucked in, then it's not going to be able to escape. Basically, if we get to the point where, following that equation, that the v, which would have to equal the speed of light, so 3 times 10 to the 8th meters per second, can't be obtained, we can get to the idea of a black hole. So what happens for a black hole is we have the same amount of mass, but all of a sudden our radius shrinks. All right? So we know, based on the idea of Fg equals big G m1 m2 over d squared, that as d gets smaller, the force gets bigger and bigger and bigger and bigger. And eventually, it gets again to that point where, based on the idea of force radial equal to mv squared over r, it hits that point where the velocity is so great that it's greater than the speed of light and you can't escape, right? Now, I see an r here and a d here. Well, in essence, that r and that d become the same value, because if you're dealing with a circle, the distance and the radius end up being the same thing for most cases. It gets a little different when we get into things like binary stars, because they might rotate a random point in space, but when you're talking like a black hole, those values are the same. But that's why I don't just interchangeably say they're both the same thing, because, well, depending if it's 2 stars orbiting each other, which could just orbit a point in space, versus a planet or a person or light orbiting a star, in that case, d and r can become the same value.